Hello guys, welcome to this section of tutorials in which we will be continuing our discussion on reviewing the basic ideas of probability. I again want to start with emphasizing that these discussions that are there are not what do you call a full fledged discussion on probability. This is just a review of things. I am again assuming that the viewers of this course are very much comfortable and they have taken at least one rigorous course on probability and then one course on basics of machine learning, and then they have come to this course on generative model. That is our preconceived assumption. Now, for the sake of completeness and for the sake of reinforcement, we are going ahead with this batch of tutorials in which our aim is to go ahead and discuss the basics of probability. Now, in our previous sections of tutorials, we discussed from the very basics the idea of probability triplet, probability space. So, we looked at conditional probability, Bayes rule, total law of probability, the idea of partitions. We looked at random variable, different kinds of random variables, in which we looked at two important things, which is discrete random variable and then the continuous random variables. We looked at the cumulative distribution function or distribution function as we call it, and then for discrete random variable we looked at the mass function, and then for the continuous random variable we looked at the density function, and then we looked at expectations. So, we looked at variance and other things. We looked at a couple of examples of these kinds of discrete random variable and then the continuous random variable. So, we looked at the functions of random variable, we looked at the law of the unconscious statistician. So, these are the things that we have looked at in our previous discussion. In addition, we looked at couple of inequalities, Chebyshev inequality, Markov inequality, Jensen's inequality, and other things is what we looked at in our previous discussion. So, we will continue from there. In today's discussion, we will be mainly concentrating on a pair of random variable, okay. So, and then we will extend it to multiple random variables, okay. So, this is where this is what will be the content of the current tutorials. Okay. Without any further delay, let us jump into the content. So, now let me define a pair of random variable. So, let xy be a random variable on the same probability space. I want to emphasize this, on the same probability space omega fp, which is there, and each xy maps omega to r. So, each one of them individually is a random variable. We can think of pair of random variable as a vector valued function that maps omega to R2. We are considering a pair of them. So, you can consider that we are mapping from the sample space to R2. Now, this is the definition. Now, how do we define the distribution function, the joint distribution function as it is called as. So, this is the notation that we use. It is a function from R2 to R, okay. So, the joint distribution function of xy. Now, how do we define it? For any given values x and y, it is probability that x takes the value less than the considered value x, and then y takes the value less than considered value y, and which can be written as intersection of these two events in a detailed manner like this. So, the joint distribution function is a probability of intersection of the events x less than x and y less than y, okay. So, when I say x, that will be the random variable, and this is the argument that we are considering, and the same thing has been written here in a much more detailed manner. So, now let us take a consideration wherein which I have x1 and x2. So, wherein which x1 is less than x2 and y1 is less than y2. Under this consideration, now how will be the probability of the random variable taking the values between x1 and x2, and the y random variable taking the probability between y1 and y2, and what is its intersection is what is being looked at here. Okay. So now when we expand this, now this is the joint distribution at the points x2 and y2 minus the joint distribution at x2 and y1 minus the joint distribution x1 and y2 plus the joint distribution at x1 and y1. Okay. Now this will be very much easy to see in the next diagram. To understand it intuitively, let us say that we have the region of interest, okay, so which is the intersection of these two. So we have I1 and I2 belongs to R. So now in that case the interval now will be in R2. So now this is what is known as the cylindrical set, and we obtain this is the region of interest in which we want to look into the probability, and then I assume that the viewers of this video are capable enough to understand this from the cylindrical set example that has been given. Okay. So now unlike the distribution function, even the joint distribution function that we have defined by taking a pair of random variable also needs to satisfy certain properties. Okay. Now the joint distribution function which is there, it is a function mapping from R2 to R, and this is how we have defined it. Now this is a valid probability measure, okay, unlike the cumulative distribution function, this is also a valid probability, the joint distribution is also a valid probability measure. Okay, it has to satisfy these properties. Now you in any one of the argument, if you consider minus infinity, so it has to be 0, so for all x and y considered, and then in both the arguments if you consider infinity, that means the whole R2 is what has been considered in this particular case, but then it has to be 1, which makes a standard improvement or the standard extension of the cumulative distribution function that we have seen. And then like CDF of a single random variable, now here also the joint distribution is non decreasing in each of its argument, exactly analogous to what we saw earlier, and then this also the joint distribution is right continuous and has left hand limits in each of its argument. Okay. There earlier we considered a scalar valued random variable, so here since we are considering two arguments, now it has to be in both of those arguments, it has to be right continuous and should have left hand limits. So if you have x1 less than x2 and y1 less than y2, now this is the what do you call the probability of that intersection of that cylindrical set that we get. Now this has to be greater than 0, which is analogous, which is just an extension of what we saw earlier. Okay. And similar to that, any function which is from R2 to R is satisfying above properties that we discussed, now has to be a joint distribution function for a pair of random variable. Okay. So now let us take the example of two discrete random variable, let x and y be two discrete random variables defined over the same probability space. X takes this x1 till xn and y takes the value y1 till ym, so there is no need that n and m should be same. Okay. So we define the joint PMF, okay, this is a discrete random variable, so we can define probability mass function since two of the random variables are involved. Now we are going ahead and calling it as joint PMF of x and y. Now this is the mass at those individual points considered. Okay. Now it is the probability at x is equal to x taking the value xi and y taking the value yj. Okay. Now this is valid for all the values that x and y are considering. If you consider any other values of x and y, now then the joint mass will be 0, you do not have any probability mass over there. So and then analogous to the mass function that we saw for a single random variable, now here also the mass has to be greater than 0 for all valid x and y that is there. For all x and y it has to be greater than, it will be equal to 0 for all other non defined x and y. So yeah, and then if you take the sum over all of them, now it has to be 1. Okay. Now this is, as I told you, this is a straightforward extension of PMF of the single discrete random variable, and then like what we saw from the PMF, so we can get the distribution function. Similarly from the joint PMF you can get the joint distribution function. So you sum it over all the values of x that are less than the considered value of x. So for example now if you are interested in, let us say that x is 5, now you consider all the valid values that the random variable x can take which is less than or equal to 5, and similarly you do it for y and take a sum over their mass. Okay. So now like this we can compute the probability that is involving two random variables. A simple example to go ahead with that, consider random experiment of rolling 2 dice. Okay. Now whenever you roll 2 dice, now what are the outcomes that you can get? Your sample space will have tuples W1 and W2 where each W1 and W2 can take values 1 to 6. Okay. Now on this sample space, now let me define two random variables. Now x be the maximum of two numbers that you get, maximum of this W1 and W2, and y be the sum of those two numbers which are there. Now it is a straightforward extension that max now which is there, that is the what are the valid values that the random variable x can take, it can take 1 to 6, it is max of them, and then y can take 2 to 12. Now these are the valid values that we can take. And then how do we define any event, x taking the value m and y taking the value n? Now what do you mean by that? Now we want those outcomes of the random experiment now wherein which the max should be equal to m and then the sum should be equal to n. Okay. Now in these two, what are the possible outcomes that are there? Now these are the only two possible things. Now one is m and n minus m, n minus m and m. Now these will, for any considered m and n, these are the only two options that are available. So when you consider n is equal to 2m, now then there will be only one outcome that is possible. Okay. So now what will be the probability? Now if you consider n to be not equal to 2m, now then you have two outcomes. If you consider n equal to 2m, so then you have one outcome which is there. So you can compute the probabilities now using these. Okay. So what will be the mass? Now for the condition m and n which adheres to this particular condition, it will be, the mass will be 2 over 36. If n is equal to 2m, now then the mass will be 1 over 36. Okay. And it is easy to go ahead and check for all the valid values of m and n, if you sum it over, now will it be 1? Now because it has to satisfy the condition. Now each of them is greater than or equal to 0. Now that is, by this definition it is taken into consideration, but there is another condition which is when you take over all the valid values it has to sum to 1. Now that also needs to be looked into. I leave it as a small exercise for you to go ahead and do it. Now let us proceed and then consider a continuous random variables. So in which case we should be defining the joint density function. Let x and y be two continuous random variables with the cumulative distribution function defined as pxy. Now when will be this cumulative function defined? If there exists this function small p xy that satisfies this condition, exactly analogous to the definition of the density function that we saw when we took a single continuous random variable. Okay. So now whenever this is satisfied, now at that case we say this small p of xy which is there, now this is what is called as a joint density function, or joint probability density function is what it will be said. Okay. And then it has to satisfy a similar condition, you integrate over the whole minus infinity to infinity in both the variables, so it has to be 1, and then at each point for all xy, now the density, the joint density which is there should be greater than or equal to 0, and any function that satisfied these two conditions is a joint density, okay, and this is an extension, exactly a similar extension of single valued random, single continuous random variable that we took. Okay. So now let us take a very simple example. Now consider a function f of x y, now which is equal to 2, so wherein which, so 0 less than x less than y and less than 1, and in every other values it takes the value 0. So now it can be immediately verified that the first condition, which is that the values that this density function should take should be greater than or equal to 0, which is taken into consideration. Now the second condition is, now integrate from x minus infinity to infinity, y minus infinity to infinity, okay. Now that has to give us 1, that is the second property which is there. Now let us see whether that second property is satisfied or not. Now integrating from minus infinity to infinity, now wherein which the only valid value it takes is in this interval, in every other place it is 0. So rather than integrating it minus infinity to infinity, I can only integrate it in the valid range, okay. Now what is the range of y? Y takes value between 0 and 1 and x takes value between 0 and y. So therefore you can integrate y from 0 to 1, x from 0 to y, you integrate this value. I am assuming that the viewers of this video knows how to at least do this integration. So it will yield us 1, okay, and the same can be looked in via this diagram, and I just want to re-emphasize that this is not the plot of density, okay. So now this is a straightforward, these two conditions needs to be taken into consideration, only then now we say that the given function is a joint density function pertaining to some pair of random variables, okay. So just a recap of the same. So the joint distribution function is integrating from minus infinity to y, minus infinity to x, you take this joint density function and then you go ahead and integrate. Now if you want to know the what is the probability in a range that x and y is taking, so you can integrate over that range and then you can get it, okay. So now let us compute another probability, let us take this example. Now let us consider the previous example wherein which we have already shown that it is a density, so I can write it as a density. Now suppose we want the probability of y taking the value greater than x plus 0.5, okay. If this is the case, what is the probability of y taking the value greater than x plus 0.5? Now then, now this is the interested event. Now those x and y are what is interested, wherein which so we want such x y such that y, the value of y is greater than x plus 0.5. So now in that case y taking the value 0.5 to 1 and x taking the value 0 to y minus 0.5. From this range, I think if this is the condition, so all of you agree to this, this will be the range in which we should be integrating. Now we go ahead and integrate, we get the probability of the specific event is 0.25, now which is, this is the region of interest, okay. So like this we can obtain the probability of any interval that we want using the defined density, joint density, okay. So now once we have this joint density, we can obtain the marginals, okay. See, the idea of marginals are interesting, so let us go ahead with that. So let x and y be the random variables with the joint distribution function given by this pxy, and then we already know this is how the joint distribution function is defined. See, what do? We take infinity at one of the variables, so then what will happen? Now this is probability of x less than x, y less than or equal to infinity, so that means that all the valid values of x are considered. Now this is nothing but now the distribution function for the random variable x. So what do we do? You just consider all the valid values of y at a given x. So that will give us the marginals, the marginal distributions, we can get it. And similarly it can be extended even for y. Okay. Now these are marginal distributions, or you can just say that these are distributions of x and y. So these are obtained, so by using the joint distribution, from the joint we got the marginals. Okay. Now similarly we can obtain the marginal mass functions. See, you can just call them mass functions. So since we are obtaining it from the joint mass function, I am prefer just to indicate that these are the mass functions that are obtained from the joints. So I am preferring to go ahead with marginal mass function. So these are the valid values that x can take, and these are the values the y can take. Now then how do we define this joint PMF? So let Pxy be the joint PMF. In that case, now how do we get the mass at a given x? So this is nothing but Px of xi, right? How do we get it? Now you sum it over all the values of y. Okay, you keep x at that specific point and then you sum it over all the values of y. Okay. Now that is when we go ahead and obtain the marginal mass. Okay. Now this, by definition, this is the joint mass. So you take the joint mass function and sum it over all the values of y, because you want the marginal with respect to x. Okay. That is what you get, and similarly this can be extended for the y also. And in exactly analogous to this, we can have marginal density also. Let xy be the continuous random variables. Now over the same sample space, I am just assuming that that is taken into consideration, so I am not going ahead with that. Now with joint density now given by this Pxy, now then this is how the joint distribution is defined. Now if you want to go ahead and obtain a distribution for the marginal distribution at x for x, now how do we do it? Now we integrate it over y. So you integrate it for all the valid values of y. Now because of which, so when you take this and integrate, now we get Px of x. So and this is what we call it as the marginal this is the marginal density of x. Okay. And similarly it can be extended for y also. Okay. See, now the idea why it is called as marginal, see earlier people used to maintain, let x, this is the column of x and this is the column of y, you have all these entries, you used to have in the margins, you have to sum it over, no. Now that is for a specific value of y, you take all the valid x's for that. Okay. You put it in the margin, so therefore these are called as marginals. Okay. Now here you fix an x and then you vary about y, you get this. Okay. That is why this is called as marginals. Nice way of putting it. Okay. So now let us try to take the earlier example of rolling 2 dice and obtain these marginals. So rolling 2 dice where x is the max and y is the sum, and then this is the joint mass that we have already defined. Now then we know that how do you get the marginal mass? You, this is with respect to x, so you sum it over all the values of y. So take the joint mass which is there and sum it over all the valid values of y. Okay. Now then you do it, so you get, I will leave the so what are the valid values that we can take? So n is equal to m plus 1 till 2m is the valid values that you can take, you sum it over and this will be the marginal mass that you get. And similarly we take the joint density and then calculate the marginal density. So this is the joint density that we have for our earlier example. Now you take this and integrate it over y. Now what are the values of y, valid values of y it can take? You have already fixed for some x, so from that x till 1 you take 2, because of which this will be the density at given x, and x can vary between 0 and 1. Now you have to verify that this is a density. Now again you take this, integrate it over all the valid values of x, and then you should get 1. In a similar manner you can obtain the density, the marginal density for y. Okay. So now if we are given a joint distribution function or joint mass function or joint density function which are there of x and y, from there we can obtain the individual distribution functions or mass function or density function. So we can uniquely obtain them. So these are uniquely determined. Now however the other way is not true. Now that means that you give individual density functions or mass function or distribution function, we cannot obtain the joint of that. Okay, if you have given joint, if you have given individual densities, how to get the joint density, that is not uniquely defined. There can be many different joint density functions with all having the same marginals. Okay, this is possible. So given a joint density or joint distribution or joint mass, from there you can uniquely determine the individual things, but the converse is not true. Okay. Now this is regarding the marginals. Now let us proceed into another important thing which is known as the conditional distributions. Okay. Now let x and y be the random variables which are defined on the same probability space. We define the conditional distribution function of x given y. Okay. Now earlier we did the conditioning of events, now we are going ahead and conditioning on occurrence of a random variable taking a specific value. Okay. Now we define this conditional distribution p of x given y like the probability that x taking the value less than x for the fixed value y taking a specific value. Okay. And this is only defined when this p y which is there, see it depends, when both of them are continuous random variables you have to define this as the density. If it is both of them are discrete, this is the mass. So okay, now that is the reason, see we can see lot of analogous things that are happening. Now therefore we use a similar notation for the mass and then the density. Okay, fine. So only when this py, the small py, only when it is well defined, now then we can go ahead and define this conditional distribution. So I urge you to go back and look at the definition of conditional probability, how we defined. Now if you are conditioning on an event b, now then that event b should have the probability value which is greater than 0. No, otherwise the conditional probability was not defined, exactly similar. Okay. So now this conditional distribution which is there, it is R2 to R is how is it defined. Okay. And this is just a notation. Now it is better you can write it like this, since it is R2 to R, now having this slash in between sometimes, so it is an abuse of notation, but yeah, we have abused notation so far very comfortably, so we can proceed with that, it will not be an issue. Okay. Now we should, even though we are writing with a bar, and we should be very much aware that this is an R2 to R function, the conditional distribution that we are defining is an R2 to R function. Okay. Now it is the conditional probability of this event x which is there, now given that or conditioned on y has already happened. Okay. Now we can take couple of examples like the rolling of dice. Now x is max and y is sum. Now x is less than or equal to 4 when y is 3. Okay. When y is 3, now then, now what is the probability that x takes the value 4, what is x is maximum. So what are the valid values whenever you throw a die, now it is 1 to 6. Now that means that for sure you get this is satisfied. Okay. Now therefore now it is having the probability 1. Now y is 9, now that means that the sum is 9. Now what is the probability that the maximum of it will be less than 4. okay. Now this will be 0, this is not a possible event. So therefore we can define the events like this, okay, fine. So for every value of y, this conditional distribution is a distribution function of the random variable x, okay. It defines a new distribution for x based on the knowing value of y, okay. Now I assume that even from the definition, now this was pretty much clear that for a fixed value of y, for knowing some value of y, it is a distribution over x. Now it is exactly similar. Now conditioned in the conditional probability we defined it conditioned on an event has occurred. Now how do you readjust the probability? Exactly analogous to this, and you can extend this into conditional mass, conditional density, so on and so forth. The conditional mass function, we define the conditional mass function of x now given y, now which is represented like this. Now you take the joint this is joint mass, since both of them will be a discrete random variable, the joint mass divided by the mass of y at that given at that considered value of y, okay. Now this is probability that x taking the value xi for a given yi, and then we can note that if you sum over all the values of I, okay. So you please look at it, if you fix a y and sum it over all the valid value of x, now you will get 1, and this has to hold for all y's, okay. So let me say that I fix y to be 3, so then what are the valid values of x, let us say that 1 2 3 something like that. Now if you sum it over you should get 1, and then whatever value of y you take, that has to be holding. Now that is what is being described here, okay. The index is this and this has to be for all yj. Now please look at the indices, okay. So and then how do you from the conditional mass which is there, now we can obtain the conditional distribution. Now you have to sum it over all the valid values of for a fixed value of y, now whatever x that you have considered, now all the xi's, now that is less than the considered value x, you sum it over and then you can get it, okay. Now a simple example that we can take is of this conditional PMF. Consider a random experiment of tossing a coin n times, okay. You have a coin, you have tossed it n times. Now x, let x be the number of heads and y be the toss number on which the first head has occurred. Now let us say that I am tossing the coin, now it is like I got a tail first, second also was a tail, the third one is a head. Now and then you stop at that 3, now number of heads you got is 1 and the toss number in which you got the head is 3 in the considered example, okay. So now in that, what is that we are asking? We are asking the mass for y given x. So x is 1, now that means that we have got the number of heads we have got is 1, okay. And then how is this y varying? The varying from 1 to n, okay. Now what will be the mass at a given k? Now the k can vary from 1 to n. Now this is y taking the value of k given 1 you go ahead and extend this, okay. So now if you have got only one head, now that means that out of n tosses if you have got only one head, now that means that you would have got n minus 1 tails. Now this is this, okay. And what is the probability of getting one head? Now out of n we know this is the binomial. Now you simplify this, you get 1 over n. Now what does this intuitively mean? If you have got only one head out of n of them, so now it is equally likely you can get a head in any one of them, okay. Now that is what it is being said. What is the toss number where in which you got the first head? It is equally likely in any of those n tosses you would have got a head, is what is being looked at here, okay. So now we can look at this Bayes rule for discrete random variables. By now you should have seen this. So the joint mass now which is there can be written as the conditional mass into the marginal of whatever, okay. So either it is if you are x given y or you considering y given x, it's fine, okay. So conditional into the corresponding marginal you can take it, okay. Now therefore you can go ahead and write the Bayes rule like this. See, I am not writing in this conditional xi, yj and other things. I think I am assuming that so we are comfortable with those notations. So you can easily see the extension of Bayes rule whenever we are having a pair of random variables. Now this can be immediately seen, okay. And the similar thing, let us do it for continuous random variable. Let xy be continuous random variable with the joint density now defined pxy. Now then the conditional distribution function is defined as this, but there is an issue. But the conditioning event y is equal to y taking the value small y is 0, has 0 probability. Now then how do you define it? Okay, you have to be writing it in terms of limits, okay. Now in terms of continuous when x and y is a continuous random variable, now this is an issue when y is a continuous random variable and then you are conditioning on y. Now y taking a specific value is 0 over there, and then if you want to define the conditional distribution itself, now then we define that the conditioning value should be having a probability greater than 0, but this particular event is actually having a probability 0. Then how do we modify the definition? So we just introduce this the idea of limiting. So we define in that case, if your conditioning random variable is a continuous random variable. Now here we have considered x and y, both of them are continuous random variables. Now in that case x taking the value less than x and then y belongs to an interval y to y plus delta, and we limit that, let delta goes to 0, okay. Now this is how we define it. This is a well defined limits, okay. So this limit exists for all y where this density is taking the value greater than 0, okay, and for all x we can define it like this. So therefore by calculating the limit we can immediately show that this the conditional distribution that is there is an integral from minus infinity to x now, and then the joint density divided by the individual marginal which is there, and then this is how this is the conditional density in that case, okay. This is how we define the conditional density. The same thing, so here we have defined it as x given y. Now similarly you can define it for y given x also, okay. So analogous to this. Now we will continue from the previous example that we had, now in which the density was taking the value of 2 with this interval which we have considered. Now we have seen the marginal densities, we have already computed the marginal densities. The marginal density of x is 2 into x minus 1 in this interval, and the marginal density of y is 2y in this specific interval. Now we have to define the conditional density. So now conditional density is the joint density divided by the marginal. So this is joint in 2 by 2y, so you will get 1 over y in this thing, okay. Again please remember this is R2 to R, okay. Okay, I am assuming that all those are pretty much comfortable by the way in which we are defining things, okay. Now what is whenever we are defining a function, now what is its domain and what is its range, so please make a note of them comfortably, okay. And similarly you can obtain the marginal density of y given x. We already have this is 2 divided by 2 into 1 minus x, so small x. So this is the marginal density which is there, yeah. And from I think these are straightforward extensions now you can think of. Now conditioned on y is equal to y, x is uniform over 0 y, okay, and then conditioned on x is equal to some x. Now this y will be uniform over x to 1, okay. Now this is a straightforward extension, now we can look at this, and similarly we can go ahead and get the Bayes rule for continuous random variable. The only thing is please take care of the in the denominator. So, you will not have a summation, you will have an integral. So, with respect to depending on whatever you are conditioning. Okay. So, x given y, you have this y given x into px. Now, this py, now py can be written as the conditional into the marginal. So, you are conditioning on x, therefore, you are integrating this with respect to x, exactly similar analogous to the discrete case, when which if you are going ahead in the discrete, you have the summation to get the total probability. Now, here you have to integrate. Okay. This is essentially the identical to the Bayes rule that we have obtained for discrete random variable. Okay. So, yeah, the only thing is wherever you had PDF over there, here you we have put PDF, wherever we had PMF. Now, that is the difference that we have done. Okay, good. See, till now, in all these pairs of random variable, we are considering both of them are of similar nature. Now, what similar nature in the sense, what do I mean by that is, x also is continuous, y also is continuous. Okay. Now, we are not going ahead with x is continuous, y is discrete combinations like that. Now, in that case, how do we define? Either we took earlier both of them are discrete or both of them are continuous. This is how we took it and obtained it, but now we are considering one of them is continuous, the other is discrete. Now, then how do we go ahead? How do we get the marginals, how do we get the conditionals and other things is what we are going to look at now. The same exercise we are going to repeat. Now, here we are considering x is continuous and y is discrete. Now, this is the condition that we have. Now, then we define x given y to be a density. Okay. Now, y, now because it is a function of x, x is a continuous one in our current thing, therefore, it is a conditional density. Okay. So, then the corresponding distribution now is probability x taking the value given y. Now, then how will be the density at a given x for a considered x? Now, how will be the density? So, now the conditioning event is y, you have to take all the y's together. Okay. Now, this is a conditional density for a given y, like that you sum it over all of them, we get this. Okay. Now, wherein which each of this x given y is actually a density. So, now y taking a value 1 2 3 with this probability. Now, then what will be the px, what will be the marginal in this case? Now, 1, now this is the conditional, this is how I have defined the conditional. So, with respect to the first conditional, the probability of obtaining the second one with respect to the second conditional, the probability of obtaining the third one with respect to the third conditional. Does this ring a bell? This is your GMMs, right? Okay. Now, remember how does the GMMs used to work? See, now consider that my data is a combination of 4 Gaussians. Now, how you used to get the density of data at that time? So, you used to think of it like I roll a die, okay, and then whichever dice has 4 sides, let us assume that. Now, whichever face comes, I go to that particular Gaussian and then I sample a data from it. Now, whenever for a given data point, now what is the probability that you get the first Gaussian into the density of the first Gaussian, the probability of obtaining the second Gaussian into the density of it. So, that is how we used to do, right? Exactly, look at this. The similar idea is what we are looking into. Okay. Now, you can, this is mixed density models, and see there is no hard and fast rule that all of them needs to be Gaussian. Okay. So, that is also fine, one of them having exponential and other things is fine, but please remember they have to be all the x's has to be all the forms of x that we are considering has to be continuous. Okay. If that is not the case, what happens? So, that is totally a different thing altogether. So, let us not go in that direction as of now. Okay. And similarly, now if you want y given x, yeah, you have to introduce the limiting factor and go ahead. Exactly the similar notations is what now we have to take. Okay. This gives us p of y given x into p of x given y into p of y, and then now each of P of x given y now has to be a valid density. Now therefore what you have to do, now you have to integrate them and then check that whether it satisfies that when you integrate over the valid range, now it has to get to 1, now that needs to be considered. Okay, fine. So now we take let us take an example for this. Okay, let us take a very simple example to understand this specific idea. So now let us take a communication system. Now we are dealing with a communication system now in which that is transmitting only two cases. One is either it is transmitting 0 volts or it is transmitting 5 volts. Now whenever it is transmitting 0 volts, the data which is considered to be transmitted is 0, and whenever it is transmitting 5 volts, so the bit that it is being transmitted is considered as 1. Okay. So now this is what the sender is doing. So now how does the receiver gets it? Now the voltage measured by the receiver is, now whatever the voltage that we get, or there might be a loss plus some noise which is because of the channel. So now let us take x be the measured voltage by the receiver, okay, and y is the sent bit. Okay. Now I want to know what is the probability y is equal to 1 given x is equal to x. So what do you mean by that? I have measured some voltage at my receiver end. Now what is the probability that the sent bit was 1? Okay, the probability that sent bit is 1 when I have measured the voltage of x. Okay. Now here x is a measured voltage. Now this is a continuous one, and y now it can take either value 0 or 1, so it is a discrete one. Okay. So now you want to find the probability y is equal to 1 given x is equal to x. So using the Bayes rule we can get this, but now what do we in practice, what do we want in these cases of situations are, see either you can get 0 or 1. Okay. Now these are the two cases that are there, and then you can immediately see that now for a given x, if the probability of that bit being 1, if it is p, now the probability of whatever has been sent is 0, it is 1 minus p. Okay. Now what do we want? We in practice we just want probability of y given x given 1 is the one that we are, it has to be greater than 0, that is all. So if you are measuring an voltage, now whatever is greater you go ahead with that is the overall idea. Okay. Now what is that? We normally what do we need in these cases? We normally just need the ratios. Okay. We do not need to compute this px. Okay. If we get the ratio, that is more than enough in this case. Now let us get the ratio. Now y given x with y taking the value 1, y given x with y taking the value 0, I expand this. Now x given y, now x given y is actually Gaussian. Okay. Now that means that if now y is 1, if the sent bit is 1, now what is the voltage that has been sent? The voltage that I have sent is 5. Now therefore you have x minus 5 here. Now if the sent bit is 0, if y is 0, the conditioning event is 0, now then the sent bit is you have sent 0 volts. Okay. Now we simplify this, now this will get cancelled off. Normally we assume that the probability of getting 1 and probability of getting y is equal, now therefore these two things can be cancelled off. So now this is exponential divided by an exponential, you can simplify this, now this will be the outcome. Okay. Now when will this be greater than 1? Now this will be greater than 1 when this 10x minus 25 which is there, 10x is greater than 25, so x is greater than 2.5. Now what do you mean by this? If the measured voltage which is there is greater than 2.5, then you go ahead and say that it is 1, the sent bit is 1. Okay. So now if x is, if the measured voltage x which is there, so if it is greater than 2.5, if you are measuring greater than 2.5, then we consider that the sent bit is actually 1. Okay. Now can I get now px? Yes, you can get px. So now this is one Gaussian, now this probability is half, again another Gaussian, this probability half. So you have to, this is the full px. okay, this is a mixture of densities, okay. You can simplify this further, I will just leave at this point, okay. Now this is regarding marginals, conditionals, pair and joints of the random variables, two random variables, pair of random variables that were considered. Now let us consider a very important idea which is independence of a pair of random variables, okay. So now let us say that we have two random variables x and y. Now when do we say that they are independent? See, the idea is very simple, you take any events, okay. If the events are independent, then now what do you mean by events are independent? Now you take the intersection of the probability of intersection of those events, now should be the product of individual events. If that is satisfied, fine, okay. That is what is being said here. So this is the intersection, the probability of intersection of now the events b1 and b2. Now if you consider them to be the product of individuals, then it is fine, okay. Now if this is true, if x and y are independent, now let us take the joint distribution. Now this is how it is probability of x taking the value less than x, y taking the value less than y. Now this is one event, this is another event, x and y are independent. Now therefore it is probability of x taking the value x, probability of y taking the value y. And what are these individually? Now individually these are the marginal distributions, okay. So now it says that if x and y are independent, if and only if the joint can be decomposed into marginals like this, okay. Now if there are discrete random variable, now then you can take the joint mass which is there. Now joint mass will become the product of individual or marginal masses, okay. Joint mass is the product of the marginals, okay. Now similarly, so let us take the x and y are discrete random variables. This is how we have defined the distribution, joint distribution. Now if this is the case, so now what will happen, the joint mass which is there can be decomposed into the product of marginals. Now then you can split this summation into the valid values of x and the valid values of y. Now we get this is, we know this is the marginals, okay, individual marginals we get, okay, yeah. So x and y are independent if and only if the joint mass can be decomposed into the products of individuals, okay. And then see I want to emphasize here for all the events, okay, it is not only for one event if you get it, no, okay, please remember this, if for all the events it has to be saved. So whatever values of x and y you take, this has to hold, okay, only then it makes sense, okay. No, just you take one corner combination of events and then if it holds, no, okay, please keep that in mind for all, okay. And similarly now we can extend it to the continuous random variables. If x and y are independent continuous random variable, now then we can go ahead and this joint distribution function is the product of marginal distribution. So marginal distribution you can write it like this, okay. Now then you can rearrange the terms and then this is what you get. Now then you can think of this as our joint density. Now joint density is the product of marginals. Now then this implies that joint density is product of marginals. Now this is what will be in case of the continuous random variables, okay. Now similarly it can be seen that if x and y are independent, so the same thing, so the conditional distribution will be same as unconditional distribution, okay. The conditional mass or conditional density which is there is same as the unconditional mass or unconditional density. This is for all x and y both being continuous, discrete and other things, any combinations that is there, now it holds, whatever combinations that we have seen it holds, okay. So now let us extend this into more than two random variables, okay. So everything we have done so far can be easily extended for multiple random variables. Now let us say that you have x, y and z, now be the random variable on the same probability space. Now we define joint distribution function like this, x taking the value less than x, y taking the value less than y, z taking the value less than z. Okay. If all three are discrete random variables, now we can define the joint mass like probability of intersection of these three events, x taking the value x, y taking the value small y, z taking the value small z. If all of them are continuous, so you integrate them from minus infinity to z in all the three variables, and then this is the joint density that has been defined, and all the conditions, that is so if it is joint mass, so at all x, y and z it has to be greater than or equal to 0, and then if you sum it over all the valid values it has to be 1, and the same thing for the joint density for all the valid values, for all the values it has to be greater than or equal to 0, and then if you integrate it from minus infinity to infinity you have to get 1. This is a straightforward extension. Okay. So now in this case we get multiple marginals, you can get the marginals like from x, y, z you can get x, y, you can get only z, you can get y, z, all the combinations you can go ahead and do. Okay. So now if you have now this is the joint distribution, on z we are having till infinity, so therefore this will become the again a joint with respect to x, y. Okay. Now please differentiate. So now the marginals now itself can be a joint of two different random variables that we have, and similarly if you take till infinity now on the arguments x and y, now this will become the marginal z. Okay. So on and so forth, and the same thing can be extended with respect to conditionals. You can condition on one event, you can condition on one random variable, you can condition on multiple random variables. So and similarly you can get Bayes rule, so on and so forth, you can just extend it towards multiple random variables very comfortably. So now what happens is, see we were taking 1, 2, 3 so on and so forth, like that we can extend it to n random variables very comfortably. In that case it is good and comfortable to consider a vector valued random variables. Okay, easy for writing, easy for notations and other things. So if you have random variables x1 to xn defined on the same probability space, so then we denote this vector valued random variable. See, I just want to put one more line here to differentiate that it is a vector. Now this is omega to Rn, and this is how we define the distribution. Okay. So you can call it joint distribution. So since the notation itself says that this is over n random variables, so we just call it as distribution functions. So I think the viewers can easily understand that it is a vector valued random variable, and then they can extend it. Okay. So then we define the joint mass or joint density similarly. Okay. So the same notation, so we use a similar notation for marginals, conditional distributions, so on and so forth. The same thing whatever we have seen, we will extend it in a similar way. Okay. So now when some of the random variables that we have considered are continuous and the others are discrete, now we do not have joint PMF or PDF. Now how do we work with those? Now we will look at it at some time. Okay. But even then if you have a combination of continuous and discrete random variables, now we do not call them as joint PDF or joint PMF, but we can still define conditional distributions. Now depending on the nature of the conditioning random variable, now we can go ahead and define it. Okay. But we can always define conditional distribution function. From there we can get conditional densities or mass functions easily depending on the conditional random variable which is there, and thus we get the Bayes rule, the total law, everything. Now you can just consider it as an extension. A simple example, now let us take that we have this joint density now which is taking the value of k in this region. Now then what is the value of k? Now this k, now this has to be greater than or equal to 0. Now then what is another property? You integrate it over all the valid range, you have to get 1. Therefore you simplify this, though this has to go to 1, you have k here, so you can easily get the value of k. And similarly, so you have this joint density you can get any marginals. So if you integrate it over y you get the joint with respect to x z so on and so forth, okay. This will be the case. Now how do we define the independence of multiple random variables in that case? An extension, a similar extension which is there. So random variables x1 till xn are said to be independent if you consider events for all the events b1 b2 till bn, okay. Now xi belongs to this bi are independent, okay. So now what do we mean by that? Independence implies that the marginals would determine the joint distribution. Again now the viewers who are cautious enough, now we said that earlier, now from the joint we can get the marginals, okay, but from the marginals we cannot get joint is what we said earlier. But what are we saying? Independence implies that the marginals would define joint distribution. Now why? Because it factors out, right. Now therefore we can easily define it, that is the only way of defining it, that is an outcome of the independence, okay. Now if x and y are independent, now then whatever it is, joint mass or joint density is factored as individual mass or individual density depending on the nature. Now similarly now we can define a function of multiple random variables. So now let x y be random variables on some probability space, let g be a function from R2 to R. Now then we can say that the z which is there is itself a random variable, okay. Now it is going from R2 to R which is a random variable. Now we can if it is discrete, now we can obtain the mass of this z taking the value z. Now what are the valid values? Now this is g of xy taking the value z. Now what are the valid values of xi and yj? Now because of which we get the considered value z. Now you take all the mass and then you add them up, you get the mass of z taking the value of that specific z, okay. So now comes a very interesting idea now which is IID random variables, okay. Now what is this? IID is independent and identically distributed. Now this is one of the cornerstones, that assumption that we will be going ahead in our discussions. IID assumptions is one of the very basic assumptions that we make, okay. Now to understand this IID assumptions, now this was the what do you call a laborious background that we just put during this whole of tutorials. So now suppose x and y are independent, okay. Now two random variables, what do we mean by that being independent? We know, and then px is equal to py, okay. If it is density or mass, so depending on the nature of x and y we can go ahead. Now then so they are independent and then they have the same distributional form, okay. So now then we call it independent and identically distributed, or we just call it IID. Now similarly we can extend it to n random variables. If I have xn till xn, or IID means individually all of them are independent, and then the pxi, now I just write it as p, which is same for all the random variables that we have considered, okay. So now if that is the case, now this is for random variables, now how will be the functions of random variables, okay. Independence of functions of random variables, how do we extend this idea? Now suppose x and y are independent, now then a function on x, g of x and h of y are independent, okay. This is a straightforward extension. So now then how they can be generalized? Now there is a very interesting theorem that now we have to go ahead, now let us do that, okay. Now suppose x and y are independent, now then a function of x, g of x and h of y are independent, Now this can be generalized. Now let us say that I have x1 till xm and yn till yn are independent, okay. Now then we define g of x1 till xn is independent of x of y1 till yn, okay, these are independent. Now in that case how do we go ahead? So the thing is, you know, one, can you get the joint density of other is what we are trying to achieve here, okay. Let x1 till xn be continuous random variables with joint density, this is the joint density which is there. So now we define y1 till yn by y1 is equal to g of x1 till xn, yn, y2, so on and so forth, we get this. Now therefore you can consider it as a vector valued random variable, so you have n of them, so we can consider this Rn to Rn, okay. So if you consider this whole transformation, or if you consider 1 transformation each of them, each gi it take n values, it takes Rn to R, okay. This is how each one of them is going ahead. Now then here you have got from x to y, okay. Now let h which is there be the inverse of y. Now that means that from y you are getting to x using this h function, okay. Now similarly you can get x1 by using this h1, hn is used to get xn, okay. So the way to write it is, you have x here, you have y here, if you want to go from x to y you use g, if you want to go from y to x we use h, okay. Now this is how you can visualize this, fine. So now then for each of them we can define a partial derivative, okay. Now we do not know the partial derivative of these functions like dou xi by dou yi. Now you define this partial derivatives. Now then we can define what is the Jacobian of this, okay. Now Jacobian we can define it like this, this is the Jacobian of it. So dou x1 by dou y1, dou x1 by dou y2, so on and so forth, till dou x1 by dou yn, dou x2 by dou y2, dou x2 by dou y2, so on till dou x2 by dou yn, so on and so forth you can assume this. So this is the Jacobian, okay. So we assume that this Jacobian j that we have is non-zero in the range of the transformation, okay. See what are the conditions that we have. So one is you have this transformation and the other is you have obtained the Jacobian, and then the value of this Jacobian which is there is non-zero in the range of the transformation. Under these conditions, now what we can do is we can say that the joint density of y1 till yn, now how do you get it? You get the absolute value of this Jacobian into the joint density of each of the ones. Now this is the inverse, this is h is from y to x, right. So you get this is for x1, so on and so forth till xn, you get it like this, okay. Now this is in compact, we represent it like this, okay. Now how do you get the joint density of a function of random variables is what is being discussed here. Now let us, to concretize this, let us take an example. So let x1 and x2 have this joint density p of x1 x2. Now y1 is g of x1 x2, y2 is g of x1 x2. So what is g1 is x1 plus x2, g2 is x1 minus x2. In that case how do we define the inverse? So it can be easily seen that how do you get x1 back from y1 and y2. So y1 and y2 plus y1 plus y2 divided by 2, what is x1 plus x2 plus x1 minus x2. So this x2 x2 2x1, therefore by 2, now y1 plus y2 by 2 will give you x1. Now similarly, so now you have this, from x you can go to y and from y you can go to x. So now what do we have? We have the joint density in this case, okay. So now how do I get the joint density for y's is the question, okay. Now I think with this example whatever I was trying to say is much more concretized is what I feel, okay. You have the joint density for this x1 and x2, so how do I get this joint density for y1 and y2 is the question that we have now, okay, fine. So y's are the function of x's, so in that case now you get the Jacobian, now you compute the partial derivatives and then so you get this is minus 0.5. Now then so you take the absolute value of it, so you get 0.5 into this is the joint density, now this is x1, now this is h of y1 y2 should be there. So what is h of y1 y2? This is y1 plus y2 by 2, so look at this is what h1, this is the h2. So now you can obtain the joint density of a function of random variables by knowing its the joint density of x1 till xn, okay. Now this is where we conclude today's discussion. See, today's discussion was much more into handling the pairs of random variables. So we discussed the pairs of random variables and then how will be the joints, so how will be the marginals, how will be the conditionals, so and then we extended it from 2 random variables, we extended it to multiple random variables and then we saw how does it work. Now how can we work with those things, and then we understood the independence, and a very interesting idea that is needed for us is IID assumption, which is independent and identically distributed assumption that is there. And then we went ahead and then saw a very interesting theorem, application of the theorem. We did not go through the proof of the theorem, now wherein which if you have x's and then you have a function, you have a transformation to y and then you have the joint density of x. Now how do you get the joint density of y is what we saw. So in the next part of this tutorial we will be going ahead with expectation of multiple random variables. Now how do they work and then what are the interesting properties now that arises because of that expectation, variance, because of which we get what is known as covariance and stuff, and then we will conclude the recap on probability with a very interesting thing which is law of large numbers. That is what lies ahead of us. So I hope this tutorial was interesting, and then I know that this is a huge list of things which we just did a recap on a tertiary overview of whatever you have already discussed. I hope this reinforced the ideas and then what conditions should be looked into whenever you are going ahead and using these ideas. I hope those things were helpful and then you learnt quite a things, okay. With this we conclude. Thank you all for staying tuned. We will meet in the next one. Thank you. Bye.